All right, we're going to begin our study on intermolecular forces, which I'll sometimes abbreviate IMFs. Last semester, we discussed what I'll call, or what is called, intramolecular forces. And these are forces that are going to hold atoms together in a molecule. So, for example, if we have a water molecule, what holds this hydrogen atom to the oxygen atom to the hydrogen atoms? We talked about valence bond theory and molecular orbital theory. We also drew a lot of Lewis structures that describe this effect. That is an intramolecular force when we're talking about the forces that exist within atoms in a molecule. Intermolecular forces is what we're going to start describing in this chapter. And an intermolecular force is going to be one of the following. Let's say we've got a water molecule here and our other water molecule here. What are the attractions that are going to exist between this water molecule and this water molecule? So this is between two different molecules. That would be an IMF, or an intermolecular force. That's the focus of this chapter. Intramolecular forces, that's what we discussed last semester. And it doesn't just need to be between, an intermolecular force just doesn't need to be between two identical molecules. It could be, for example, between water and a molecule of methane, for example. As just one example. As you can imagine, there's a lot of different interactions that could occur between a whole bunch of different chemical entities. For example, we could put a chloride ion here and ask ourselves, what are the forces that exist between the water molecule and the chloride ion? This would be an example of what we will call intermolecular forces. So we're going to discuss the different intermolecular forces, and the first one that we are going to deal with is called an ion-dipole attraction. This is the first of our IMFs. And what's nice about the name of many of these IMFs, or intermolecular forces, is that the name tells you what's going on. So in an ion-dipole attraction, what we have is an ion. Could be a cation, which you'll remember is a positive ion like sodium, or it could be an anion, a negative ion like the chloride ion. And that ion is going to be attracted to a dipole. What's a dipole? You might remember we were discussing polar compounds that a dipole is a molecule like water that has a partially positive part. Remember, those hydrogens on water are partially positive, and a partially negative part. Any of these molecules that have this partially positive and partially negative part, we call those dipoles. They're polar molecules. So water's a polar molecule. And polar molecules are dipoles. And just from electrostatic interactions, remember opposite charges attract, we're going to know that part of this water molecule, you should know which one, is going to want to be attracted to the chloride ion, whereas another part of this water molecule will want to be attracted to the positive sodium ion. If we remember that opposites attract, you'll recognize that the hydrogen atom on the water will be attracted to the chloride ion. The oxygen atom on the water molecule that's partially negative will be attracted to the sodium ion. And so we could set up two different ion-dipole attractions. I'm just going to draw the attraction here by a dot here, signify it by a dot. This would be an attraction that we would expect. We'd expect the hydrogen atoms on water to be attracted to a chloride ion. And we'd also expect the oxygen atom on a water molecule to be attracted to a sodium ion. And this would be an example, or two different examples, of ion-dipole attractions. You have an ion that's attracting to a dipole, our polar water molecule. So this is the first of our IMFs that we're going to learn about, ion-dipole attractions, the attraction between an ion and a polar molecule. Obviously, this is important with substances dissolving in water. All right, let's move on to our second intermolecular force. Our second intermolecular force that we're going to discuss is called a dipole-dipole attraction. And this is another one of those cases where the name tells us exactly what's going on. Remember, a dipole is a polar molecule. One of these molecules, it has a partially positive and a partially negative part. So this is one of our dipoles. And then we could set up another molecule that's a dipole over here that has a dipole. I'm just going to put a molecule of acetone over here. Here, the carbon is partially positive and the oxygen is partially negative. So we have two different dipoles, and they're going to be attracted to one another. Now, not in the orientation that I have here, because you'd have a negative being oriented towards another negative. That's probably not the way that these two molecules are going to interact. The way they would probably interact is we're going to have let's do our methane over here, like this. And we're going to remember that our oxygen's partially negative, and that's going to be attracted to the hydrogen atom of a water molecule. We can signify the attraction with sort of a dotted line here. This would be our expected, or an expected interaction between the negative portion of the acetone dipole and the positive portion of the water dipole. So this would be an example of our second intermolecular force that we're discussing, which is a dipole-dipole attraction, the attraction between two polar molecules. The partially polar part, positive part, I should say, of one of the molecules is going to be attracted to the partially negative portion of another molecule. So what I want you to do at this point is just stop the video and think about how you would orient two water molecules to each other. If one water molecule and another molecule were going to interact with each other, what might be the way those two water molecules would orient with each other? Stop the video, draw out some possibilities, and we'll pick it up in a bit. Okay, let me draw what you should have come up with for possible orientations. It doesn't have to look exactly like what I've drawn here, but you should have some sort of interaction where the hydrogen atom of one water molecule is oriented toward the oxygen atom of another water molecule. If you have something that looks like this, you know what you're doing in case of the dipole-dipole attractions. All right, the third intermolecular force we're going to discuss. This one, the next two are kind of subtle. This one is called a dipole-induced dipole interaction. Well, I already know what a dipole is, so let's just draw a water molecule in here. I'm going to draw it like this. And for the other molecule, what I'm going to do is I'm going to draw a molecule of carbon dioxide. I've drawn carbon dioxide because we know it dissolves in water. If it didn't dissolve in water, we wouldn't be able to enjoy the fizziness of soda pop. But from what we've learned to this point, we might assume that carbon dioxide could not dissolve in water, even though it does, because we have a polar molecule over here with the water and a non-polar molecule over here with carbon dioxide. And we know that, with a simple explanation of like dissolves like, we might expect that the carbon dioxide would not dissolve in the water. And yet it does. The reason why it does, or I should say part of the reason why it does, is because of this dipole-induced dipole interaction that occurs between water and carbon dioxide. Now, to understand this, we're going to have to imagine an electron cloud around the carbon dioxide, a molecular orbital. And, the electrons are going to exist in that molecular orbital, which is going to sort of exist as a cloud around our CO2. And let's imagine this water molecule coming close to the molecule of carbon dioxide. So it's approaching. What's going to happen to this electron cloud as these positive hydrogens from the water approach the CO2? Remember, electrons are negative, so this electron cloud is negative. Well, if opposite charges attract, that electron cloud is going to get pulled toward the hydrogens. So it's going to look something like this. I'm going to leave out the designated positives here. This is a huge exaggeration what I'm drawing here. All right, let me draw my carbon dioxide molecule here. And let's draw our electron cloud distorted. It's going to be attracted like this. This is a huge exaggeration just to make the point. But of course, that electron cloud, which is negative, is going to be attracted to these hydrogen atoms that are positive. And so what's going to happen as a result of this shift is this end of the molecule is going to be, these are negative signs, are going to be more negative, and this region over here that doesn't have the electrons around it, so many electrons around it, this is going to become slightly positive. It's going to be just a small shift. So it's going to be a small negative over here and a small positive over here. But the effect of this interaction is that this dipole here has caused or induced a dipole in the carbon dioxide. And so by the water interacting with the CO2 in this fashion, we see that the water molecule can induce a dipole in a nonpolar molecule and thereby cause an attraction, right? Because we know this is positive here, partially positives. And now that this is partially negative, there can be an attraction here. So this is the basis of the dipole-induced dipole interaction, where a molecule that contains a dipole, which we call that polar, is going to induce or cause a dipole moment in a molecule that doesn't have, at the beginning, doesn't have this dipole moment. Remember, we call those nonpolar. So this is an interaction between polar and nonpolar molecules, where in a sense, the polar molecule makes the nonpolar molecule a little bit polar. So this is our third intermolecular force. Our next intermolecular force is even more subtle than dipole-induced dipole. This last one is called the induced dipole induced dipole force. Sometimes these are called London dispersion forces. You might hear it called this. You might also hear them called van der Waals forces. So what in the world's going on here? Well, in this case, what we're going to have to do is we're going to have to imagine a molecule with an electron cloud. Draw it like this. I'm just going to draw it as a circle just to keep it simple. And that electron cloud, or molecular orbital, however you want to view it, is going to have electrons dispersed around it. And we can imagine those electrons dispersed evenly throughout the electron cloud or the molecular orbital. However, there is a chance or a likelihood that these electrons are not distributed evenly around the molecular orbital. So I could have drawn things like this, based on random fluctuations. It might be the case, 1, 2, 3, 4, 5, 6, 7, 8. It might be the case that the electron distribution is more like this. Now here, if I look at this even distribution, we'd say, well, there's no part of this entity that's more positive or more negative than the other. But over here, with this non-uniform distribution, we'd say, well, with more electrons over here, this part of our molecule, again, which we're representing as a circle, is going to be slightly negative, and this part is going to be slightly positive. So we would call this an induced dipole. And this induced dipole just arises on these random fluctuations alone. And now we're going to imagine taking this induced dipole and bringing it close to this molecule over here. So we're going to bring these together. If we do that, we move this over here with the negative part over here and the positive part over here. Let's imagine what's going to happen to these electrons as this entity is brought closer to it. Well, with all these negatives, these electrons are going to want to move away. So what I would draw here is the following. As this comes close to this, it's going to look something like this. Let's put our 1, 2, 3, 4, 5, roughly 6. That's representative of this. Here, with these electrons close to it, the electrons over here are going to want to move away. Of course, not all of them. 1, 2, 3, 4, like that. So this has a partial negative and a partial positive like this. And now, because this induced dipole has moved closer to this nonpolar entity, we see that this induced dipole has induced a dipole over here. So we make this partially positive and partially negative. And so we see that now this induced dipole can be somewhat attracted to this induced dipole over here. And this is the basis of our fourth intermolecular force that we're discussing, which is called the induced dipole force. And this would occur between two molecules that are nonpolar. So for example, we're going to remember this is the Lewis structure for nitrogen, which is a nonpolar molecule. And if nitrogen molecules could not attract one another, then it would be impossible for nitrogen to form a liquid. Because remember, in order to form a liquid, you've got to get attraction between molecules to get them out of the gas phase, to attract to one another, and to enter the liquid phase. So without this force, liquid nitrogen, one of our favorite substances, of course, could not exist. So the induced dipole force, or London dispersion force, or van der Waals force, which causes nonpolar molecules to have some attraction to one another, makes it possible for entities like liquid nitrogen to exist. Now this effect, this induced dipole force, is strongly influenced by what's known as the polarizability of an electron cloud. And all this means, polarizability, all it means is how easy is it, how easy it is to move around an electron cloud in something. So for example, let's say we have our original substance here with our 8 electrons in it. If it's easy to have these electrons move around, we would say it's polarizable. Then it's quite easy to cause this shift that we're talking about, where part of the molecule can be somewhat negative and the other part can be somewhat positive. And if you have this effect, then it's easy to set up these positives and negatives, which then allow this to be attracted to other positive and negative charges. If something's not polarizable, so this is not very polarizable, not very polarizable, then in this case, it's very difficult to get this electron cloud to move around. And so you're only going to cause a slight shift. So just to designate this, I'm going to move this electron over in this direction, but everything else pretty much stays the same. All right, this one's going to shift, so we're going to move this one over here. And in this case, it's pretty much the same thing. It's almost as if you get no shift of the electron cloud in this case. So we would say this is not a polarizable entity. We should recognize that the polarizability of a substance is going to be influenced by quite a few things, but mostly what we want to remember, it's going to be influenced by size. Let's show why this is the case. Let's imagine we have an atom of helium. So it's got a +2 charge in a nucleus, and it's got 2 electrons that are in the 1s subshell around our +2 nucleus. So these electrons are really close to the nucleus, strongly attracted to it. On the other hand, we could imagine a atom of xenon, which has a +54 nucleus, which is, it's substantially larger. But there are electrons in shells. Let's see, that's the first shell, second shell, third shell, fourth shell, fifth shell. We've got electrons way far away from the nucleus that are going to be shielded, especially these, valence electrons. They're going to be shielded from the nucleus by all these core electrons. And so it's going to be, obviously, we remember it's easier to remove these electrons, and just like it's easier to remove them, it's also easier to pull on them. And that makes it more, it makes it easier for these electrons to move. In other words, shift. So we would expect that xenon is much more polarizable than helium. And this tends to be the case with size. The larger the substance, the more polarizable it tends to be. And this, of course, has an impact on the boiling points of these compounds. Helium, if you imagine liquid helium and we want to boil it, well, we'll imagine taking everything down to below its boiling point. We'll just say for helium, you got to cool it to below 4 Kelvin to get it to liquefy. So heating helium just to 4 Kelvin causes it to boil, to enter the gas phase. And this is a direct result of how difficult it is to polarize helium. If it's difficult to polarize it, it's difficult to set up these small positive, negative induced dipole interactions. So you're going to have very little attraction between atoms of helium, and you're going to have an extremely low boiling point. On the other hand, xenon has a boiling point of 165 Kelvin. It's still low. I mean, that's colder than dry ice, but nevertheless, it still shows you that you can keep xenon atoms together in a liquid at much higher temperatures than helium, and that's because the xenon is so much more polarizable that you can set up these positive-negative induced dipole interactions, allowing these atoms to attract and remain in the liquid phase.